Okay. So yeah, like I said, we are going to be working on that Wi-Fi module. That's going to be a part of the bigger project. So basically the idea that I have is, can we see it? Yeah, we can. So basically the idea is I have this camera, and so I have this camera and the request of my daughter to build a bird box, because you know the bird's gonna have to earn the shelter and the food that we're going to provide, and we're going to play a little Big Brother. So basically we are going to install the camera in the bird box. So I want to use the wireless Wi-Fi module to be able to stream the data from this camera and hook it up to, I don't know, my website or something like that. Not sure yet how I'm going to do this, but basically the idea so far is that the camera is hooked up to the blue pill, or not the blue pill, the black pill, because I have a couple of those black pills in here. It's the STM32F411 that's on it. So can I boom, that's basically what we have in here, and that's the module. So ESP01S with Wi-Fi module hooked up to the black pill. So first of all, I just want to start just to get the serial stuff working on the chip. So we're going to start simple by getting the serial stuff working on the black pill. We're gonna hook it up to the PC initially through the RS232 to USB cable. So once we are able to communicate with our serial terminal on the PC, we know that works. After that, we will hook it up the Wi-Fi module over the well, we're going to hook it up to the same cable and see if we can talk to this like that. So then we know that both of the parts of our setup works, and we will get the black pill talking to the ESP01S. And then once we have this communication working, we will look at getting the camera working. We'll see if we can capture some data out of it and then stream it across the Wi-Fi module to wherever we want. So obviously there's no way that we're gonna get this all working today. So today I think it's going to be a success if we get the serial working, and if we're going to be able to at least start talking to the to our Linux machine. So I decided to do everything from scratch, as I usually like to do. So just so that we can review where is the Rust ecosystem at the moment right now, because the stuff is changing really quickly in there. It's a little bit like JavaScript ecosystem. You just can't keep up, but it's a good thing. I'm not saying it's a bad thing. It's a good thing, and stuff is really getting stabilized in there. So for example, we are going to be using the Arctic, and as you can see, the Arctic was just stabilized at the end of the last year on the version 1, which is a very good thing. So we're definitely going to be using this. The next thing is the STM32F4XX HAL. So there's stuff definitely going in there. It's actively developed. So we're going to have a look at this as well. This is just definitely going to come in handy for the chip that we're using, the 411. Yeah, and I think we're ready to go. And one other thing is that we're just going to generate the project from the scratch essentially. So dev cargo. I recently started using this thing, cargo generate, and this is a template that I've created for the STM, for the quick starting of the STM projects, so that by default it just configures the stuff ready to roll for the STM32 family of chips with the RTIC. So what are we going to be doing? So we're going to be looking at birds. So the glare without DRS. Yeah. The glare. Actually, maybe I should move this to where I keep all of my embedded stuff. Okie. So since we created it from the template, we already have stuff pre-configured in there. So we have our cargo config configured with stuff. Oh, actually, one other thing is I started using this probe. What's the exact name of this? It's from Knurling probe. Yeah, this thing, probe RS. So it's a cool little tool. I've only started using it, so I'm not all that familiar, but it makes stuff way easier to work with. Basically, you can just hook it up directly into your workflow when compiling and loading the code directly into your chip. I'm just gonna disable this a little bit. Okay. So yeah, that's definitely worth checking. So we actually have to configure a couple of stuff in here anyway. So definitely let's check on cargo. So yeah, that's this Cortex, yeah, one. So I created this in a template because I knew I'm gonna use this mainly, like this. Cortex RTIC. We're probably gonna have to add embedded HAL into this, and that's on version 02.6, I think. Actually, maybe I should do it like this. Okay. How did you name it? Glare. So this can be working away. So we're going to be needing embedded hole, this. Okay, that's it for the time being. We need to be definitely editing, because if we use the cargo generate stuff, so like it generates or it grabs most of the files from the template, but you still have to fill up some of those details. So one of those details is the memory stuff. So what was it? I don't remember. What was the size? It's 512, I think. Yeah, it's 512. Okay, and the RAM is 128k. Okay, this, and what else we need in there? So that's, we're not going to be using any of this. Oh, we might need to do this. STM T2 this. Yeah, like this, and we will need the so yeah, that's our crate going for lib. Okay, and nice, so we're good to go, I think. Let me just double check. Memory source. Yeah, we edited. Oh no, yeah, exactly. We need the cargo as well. Cargo config. We need to specify the chip here. Yeah, and I actually stick it. I already put it into the template, because I have a bunch of those black pills that I bought before the pandemic, because right now they're like the blue pills and the black pills, it all went so up, the prices for it. But I managed to get a bunch of those. Yeah, it's like toilet paper before pandemic. Luckily. Okie dokie. So this. Yeah, so this, and we are not compiling. Oh no, we're compiling. Okie dokie. So yeah, we haven't saved this. Okay, is everything okay? Yeah. Okie dokie. So first of all, we want to get the serial working, and we wish to be able to communicate with the computer. Oh, and the music wasn't working. There. A bit of John Carpenter for the nice flow of code. There. Okay, so let's grab we don't need this, not this, not this. So I want to be able to just get the serial working first. So we go to examples and we go to So USART blah 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 blah. That's just one pin. That's a one pin setup, just for the transmitting. There was this. So that's a transmit and receive pin. This is for the 9-bit word size. We will adjust the example as we need it. So we need this and this. Okay. So idle, and we need to stick it all in it. Okay. So I haven't been messing around with this in a while, so I will need to refresh everything a little bit for myself as well. So we will need the context. We need to get the GPOA peripheral. GPOA, and that was coming from context. Dot device, I think. So actually no, that was device peripheral. Okay, and now we need GPOA is dp.gpoa, I think. Isn't it? Yeah, dp blah blah. Do we need split? Okay. Okay, I think we need a couple of imports. So use this, how what was it, prelude. I'm not exactly sure where that split function is defined. Okay, and we need serial. Hey, that example is a bit weird, isn't it? So there's a serial trait implemented onto the USART peripheral. This crate is a little bit different than the F1 STM32F1 hull that we've used. So there is no serial in there. There is, and it has a new. Okay, so I will stick to what I'm familiar with. So serial and new, because I'm not sure where to import that. What interface do I need to import for it to work? And this takes the USART. So in our case, it's going to be. Oh, actually, so this is the thing that we haven't thought about yet. So we want pin out and pin descriptions. So this is our chip. Isn't it? Yeah, I think that's the one. No, that's not the one. I think it's this one. Because that's the 16-bit. So this is our one. So we are looking for the pinouts. So I want to be able to have one full port available for the camera interface, because we will need the SPI or I2C. I don't remember what it's there here. So we will want a port for the control interface for the SPI, I think, in that case. Yeah, and we want 8 pins for the parallel interface for the data handling. So I want, let's say, the way it is on the board here. So I will use let's say 0 to 7 for the parallel interface. So in that case, I think, because this is using the UART tool, was it? So is there a UART 1 available somewhere? It's USART. Yeah. So there's definitely USART on pins 9 and 10 on the port A. So CK on port A. So yeah, PA9. We have a transit and a receive. So PA9 and PA10 on USART 1, and I think that's what we're going to use. So just to have it ready, I had a couple of, I don't know, should I be showing this crap when I mess around with pinouts? So we will need a ground in here, because the common ground is extremely important. And then the orange and yellow were the transmit and the receive, but I don't remember which one is which, so we're just gonna have to try. So the PA10 is a receive, so we will try this as a receive, and we will try this as a transmit and common ground. We don't need the VCC, even though it is 3.3 cable, and it's a 3.3 actually I think it's at 5 volt tolerance, so we would be okay, but 3.3 is also fine. So actually what we want to do is the PA10 is receive. So PA10 and this is 9. Okay, and that means this is a USART 1, which we will need to import. USART 1, and we need serial config. And what else we need? Use create must enable RT feature. Yes, okay. We're compiling. Yeah, so we need clocks. Expected value found struct USART. Expected value found struct. What's wrong with here? Oh, that's because we want an actual device instance. Like this, and we need, so this is unnecessary, and we need the clocks. But where did the clocks come from? I never remember clocks. So that's what dp.rcc. No, let's have a look here. One of the old ones. Ah, yes. So we need rcc constraint. So, and that's our RCC, and then we need clocks RCC dot CF, what was it? CFGR configuration, yeah. And let's use high speed external and 25 MHz, and we need to unwrap it, yeah, or freeze it. Okay, so that's better. So we have our 2 pins, we have our serial, yeah, because we don't use this anymore, and we don't use 9-bit words. We use the standard 8 bits, and type what notations needed. I would expect it to figure it out. not infer type. Consider giver blah blah blah. It's complaining about the word size. Okie dokie. So we don't care about this. But we do care about the interrupt. So we like to be able to receive this stuff. So we need to configure the task which is going to be bound to the USART interrupt. And just to make sure that we're looking at the right interrupt, we wish to use the USART. There is one, and it's the one that we're using. This. Okay, so what was it? Task. Let's check the examples because I don't remember. What was it here? The hardware task. Idle, yeah, task, and then binds and whatever variable, whatever messages we want to pass into it, or variables. So task binds and whatever the peripheral we wish to bind the interface to. So in our case it's 1, and again we don't, well, right now we don't care about those. And it has to be specific naming, so USART handler, I guess. Actually no, because the naming of that is what we what's going to be passed in here as the argument to the handler. So that's our context, and that's going to be USART on context. And there's nothing coming back out of that. Yeah, because it's USART. Okie dokie. So what we will do, we wish to transmit and receive, well, I'm not sure if we wish to, but I want to right now, because I don't want to be forced to be passing around the RX and TX all over the place. So we are going to just push this in here, the X and RX. So basically we will just be sending and transmitting only from the interrupt handler, and we will use some sort of queue to be passing the data that we receive or that we want to send using that buffer between the other tasks. And so for that we also wish to configure the listener or the interrupts. So we use serial dot listen. No, what was it? was here. Serial. And the interrupts is listen, and we need to specify the event. And the events are this and this. We don't care about the idle. So we wish to trigger interface on both list, transmit and receive. So transmit is whenever the buffer is going to get empty. That triggers the interrupt so that we can push the next data to send into the internal hardware buffer. And receive not empty, so that's if we have something that is coming to the serial peripheral. So basically that means that we have a byte of data awaiting to be read. So listen, and that's event. What was it? ESP server event, and RX. What was it? Serial event, yeah. RX not empty. So that's correct. Yeah, it's complaining because we that's in a second, and then we wish a second one as well, but this one is the tx empty. Yes, okay, so we have this, and that means that here we should be able to just interact with the peripheral within the interrupt. So actually let's fill in those structures first. So that's going to be local, because so basically the local is the variables that you wish to pass to a single task, and it's not going to be shared with any other task. So basically there is no need for any extra additional locking or anything like that. Shared is a structure of a variable that we wish to share between multiple different tasks, be it a software task or a hardware task or whatever. But that means that since we agreed that the TX and the RX we're only going to be using within the interrupt, we can stick it into the local. So TX, and this is TX and RX, like that. So TX and RX is RX, and what does it need in there? It needs the USART, yeah. Split. So it needs USART and a word, and we see that the word has a default value, so we only need to specify the USART. One, and it's the same here. Okay, and now we need to stick it into our structure. So TX and RX, and cannot borrow as mutable, yes. Okie dokie. And user blah blah blah. Yeah, so we just have warnings related to the ROS being anal about unused stuff. Okay. Yeah. break. I'm going to be disgustingly munching on an apple. So get ready for some sound effects. Okay, we're good for now. So, we wish to be able to have some sort of communication now. So we need to add some buffers. So there is a library called Hipless that has a bunch of buffers that we can use for that. Actually, let's see. Yes. Okay. It's a nice library, and we used it before in some of the other streams. It has a bunch of, well, as the name suggests, heapless vectors, and I think there's a hash map in there or something like that for storing data without a heap. Okay, so we will need those queues now. Heapless, and we need the single producer, single consumer. We need producer, and we need consumer. Yeah, and we need to stick them into the queue, but the great thing about it is that it has a, it's basically, there's a queue and which creates a producer and a consumer. So even though the queue is shared, we don't have to stick it up into our shared structure, because we will just utilize the endpoints, which are separate structures that we can talk to and read from. So this actually needs also a queue. So in that case, in here we can stick out the, so we will have one queue, no, we will have two queues, and each with two endpoints. And so basically one of those queues is going to be for incoming messages and one for outgoing messages, and each of those is going to be a producer and a consumer. So we can think of it as a transmit producer, transmit consumer, and then Rx producer, and Rx consumer. And each of those is so that's a producer, What data does it need? API reference. It needs the size of the queue and the type, isn't it? Yeah. So right now we're just gonna be sending bytes, and so const queue when that's going to be 8 as well, and let's say 8 for the time being. Yeah, and this is going to be a consumer, or a consumer with exactly the same arguments. And that's again, that's a producer, 8, and that's a consumer. 8 and QN. Expected a lifetime. Okay. Static should do. Yeah, that's just maybe silly. Not everything in embedded has to be tiny. Okay. So now we need to create those. So let rx q equals q ht q. Okay. Q new. Now we need to create the specific endpoints. So rx prod and rx com, and that's the rx q was it split. Yeah. Yeah. And we'll just stick this in here. Xcom, tx prod, rx com, and rx prod. Okay. Okie dokie. Yes, of course. is this? Does it need to be or not that? What do you mean it doesn't leave it long enough? Oh yeah. Oh really? I hope me munching on that apple doesn't make people sick. Okay, yeah, anyway. Doesn't live long enough, blah blah blah. Okay, yeah. We can solve this out with singleton. What's this from here? Where do I find the singleton? There's a bunch of those. It wasn't hitless, it wasn't here. I think that was coming from cortex singleton. But I don't remember what was the syntax of it. It needs the cortex and it needs a specified type. I just forgot what the syntax of it is. Okay, so just a thingy and a thingy. So we are specifying a queue like this, and that was U8 and Q1. Yep. Okie dokie. And blah blah blah, and we need to unwrap it. This. Okay. So we don't need this to be immutable after all. And same here for now. Okay. So that's starting to take some shape. So it's complaining that the stuff has been never used. That the stuff has never been used. So yeah, start using those. So how do we want to do this? So we will need to go into the interrupt and check for the bits to be either set or not, and and just basically push the stuff into the queues, and that's it. I don't think there's anything what's the word, sophisticated needed in there. So okay, so this is the interrupt queue. So in here we will need to talk into the receive queue. So we will need Rx producer, and we will read from the transmit queue. So it's going to be TX consumer. Okay, and so that means that we need to get the two endpoints, or the two peripherals. So let tx is tx.local.tx, and this, and now we need to get those queues as well. So we're getting into the interrupt handler, so we will unlisten and Rx unlisten. So we need to disable the two interrupts, and at the end we will enable them back again, and in between or here even, local variable with similar name. Yeah, what am I doing? Oh, that's me just being uber silly. Yeah, and in the meanwhile, so if we need to check if those interrupts actually occurred, because this handler is shared between all of those interrupts for this particular peripheral. So if we enable the third interrupt for the idle, it would all have to be handled in here, and this is why we need to check which specific interrupt was triggered. And so in order to check it, we need to see this is the TX empty. Is TX empty? We're going to handle it in here, and in case of receive is where's my music? Of course, watching. Why post? There. Okay, and in this case it's is Rx not empty? Is Rx not empty? We're gonna do some other stuff. So if the TX is empty, so if it's empty, read whatever we can from, or whatever is available in the queue. So a byte, because that's all we can. This is the word length, so that's as much as we can send at one time. So local, and we read it from our txcon, and into the queue the queue, and so yeah, that gives us option. So if we have something, we read it, and we need to write it into the UART peripheral. So tx dot just write nr byte, and we're probably gonna have to unwrap it or something like that. Yeah, unused thingy. Yeah. And here we have a slightly separate, or we have a slightly opposite thing. We read from our peripheral, and if we have something, and we know we have something because the RX DR buffer or whatever that register is called has been filled, so and the interrupt has been triggered. So in this case, we just need to grab the handle for the queue and stick our byte into it. So that's our byte. We're going to read it, and then we can just stick it in. ctx.local. What was it? It's the RX prod, and it's NQ. That gives us result. So probably gonna have to handle that as well, but first let's see. Like that. Oh yeah, and that's a result as well. So okie dokie. So right now we're reading and writing into the queue, and in here we just continuously want to read out of the queue or write to it. So for the time being, I guess we can start from just like a simple echo, so that we want to be able to just read and write to. So we will type in the terminal, send it to the microcontroller. Microcontroller will just read it and send it back out. So we don't need this. So for the time being, we can maybe just write something. What was it? Print line. So hello idle task, and here it's just similar. We will check the RX queue to see if we got something from the Linux, and if we did, send it back. So basically, if so similar way, byte is so we need to actually let the idle task know what are we going to be using. So here it's going to be RX consumer, because the producer is in our interrupt routine, and this is going to be producing stuff for the TX queue. Prod. So ctx.local. Here we received first that and the queue. So if we got something, should we print it? empty print line got byte and then ctx dot local dot tx prod and nq byte. DFMT like that. That's CX. Ah, yeah. I have to be more consistent. Like that. And that. Like this. Okie dokie. So unused result at 86. Yes, with that, and that compiles actually. Okay, I need to clean my cat litter box because that fucker just put the most smelliest crap ever. So BRB, I guess. Okay, back. I have no idea how cats can, you know, compact in one package something so disgusting and so cute at the same time. Okay. So I would say that we should be good. Like that. So hopefully. So we should be good to go actually. I'll just put this on so that maybe you can see me messing around. So we need to change this actually. Oh, actually there's another mistake because we're not using word length, and we want the baud rate to be 115/200, like that. And actually with the probe now what we can do is specify a cargo watch and -x like this RRB, and in our case it's just main, I think. Target main, well, what was it? it's our alias. So RB main, yeah, it should be main. Yeah, actually, let's check it out. Cargo RRB. Oh no, it's not main, it's whatever we named it. Glare. There it is. Yeah. It's just that we want to do this in the watch. Yeah. Like that. So that will configure it in a release mode. And what's going on? Oh yeah. That will compile it in a release mode. And when successful, load it into it won't, because I haven't connected it. Damn. Boom. I forgot to plug in the SD-Link. Why do I have an error here? Oh, it's the Rust analyzer not dealing correctly with the macros, I think, still. Yeah, but anyway, that's the stuff. So basically, if we're successful, we should be able to see this being printed and some bytes being sent. So we disable interrupts. If there's something to send, we send it. If not, we receive it. And then we restart the interrupt pack. And it doesn't work. So we probably reversed the takes with the transit would receive. Nope. Oh, program panicked. Hard fault. Where is that? Framing. Failed at result. So cargo RD glare. Success. Fin. Is our ground correct? Yeah, it is. Okay, let's check again. Oh yeah, I crashed it when disconnected the pins. Okay, so maybe it's not all that bad. So it's flashing in this part is success, and it's not crashing during the operation. So we can type anything. So what is going on? So it's flashing. Okay, so the idle is not sending anything, so we won't be worried about the interrupt yet. Yeah, first of all, let's make sure that we are actually like that. So hello from init. So we're initting, but we never go into the idle task. We never go into the idle task. Oh, hello, Alex the Fluff. So right now I'm just working on getting the serial working or going. So we configured the STM32F11 F411 with some serial handling code, and we're just trying to get it to talk to the Minicom on a Linux over a serial. Yeah. So the thing compiles, but we have some issues with getting into the idle task. So I think the issue might be right now with our interrupts. So let's just see if we can get rid of those. And we'll see if we can get into the idle task. And if hello from idle task. Okay, so our problem is our interrupt. So let's think what's going on. We're not crashing definitely, because we're only using the unwraps in here. So if we crashed, we would see the panic. So that means that the code is working, just not doing what we expected to do. So we disabled the interrupts, and we know that the stuff is getting into the idle task. So that means what does it mean? So that means that something is starving the idle task. So if we go and listen and we get rid of this, will that work? Yeah, that works as well. Can we send something? We can't. Is our Minicom working correctly? Okay, so this is a little too small. Let's do it like that maybe. I'm hiding the output of this, but it's fine. So we need to maybe we're talking too fast. Clear, hang up, blah blah. Local echo or on and off. Okay, so we're not now know that we are actually sending. So hello from init, hello from idle task. So in that case, so that means that our interrupt only fired once in here. So okay, so let's do it differently. Let's only focus on one interrupt for the time being, and see if we can at least receive. So we get to init, but we don't get to Rx. Okay, let's make sure that the ports are actually okay. Yeah, we crashed the program again, but it's fine. Okay, so in this case, let's do it differently. Let's first check that we can send. So we're going to transit, and then what was it? Right. Yeah, right all. Let's do it. Hello. Can we do it like that? Yeah, it needs to be multiple. And the usual. Hello from in, and we receive the hello. Okay. So that means that our Rx and Tx is correct. And we even went into the idle task. Should we maybe add carriage return? Is this the problem? Or is it add line feed? Okay, maybe that was the problem. So let's restart this. Okay, we're sending hello, and we got into the idle task. So got byte. Okay, so let's be explicit in here. Got byte. Otherwise, no byte. And in this case, so let's say so text interrupt. Oh, okay. Oh, so that means that this is being constantly triggered whenever there's an empty buffer, and it will be, because we start with the empty buffer. So that means that we are hitting this interrupt constantly, and that's why it's starving the idle task. So we have to restructure our application in this case. So what we want to do, we want to the microcontroller is not going to be initiating the communication with the PC. We wish to initiate the communication, so we don't have to enable the TX interrupt right away. So what we can do is that we can enable the TX interrupt whenever we want to await for something to be sent. So in this case, let's grab this. So if there's something to be sent or to transmit, and then we disable the transmit interrupt, and then we start listening. After we successfully sent the data. So we received something. We encode it, and then listen for more. So actually no, and then TX listen, like that. There. So we always want to listen for the RX, but we listen for the transmit only when we expect to actually get something. So that means in here we don't want to span like this anymore, like that. Should we maybe just restart it, because I'm not sure what was going on there. So there, takes interrupt, blah 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 blah, we have hello, and then okie dokie. Oh, so we need to disable the local echo. Boom. Okay, so we were simply going too fast with our interrupts, you know, recklessly, I should say. Yeah, okie dokie. So basically now we are able to send and receive data between just using the serial essentially. So right now it's between the PC and the microcontroller. So this is the first step. So we will be using a microcontroller to talk to the Wi-Fi module over the serial. So now let's make sure that our the Wi-Fi module also works. This thing. So toilet break. Boom. And we're going to hook it up really quickly to the serial cable, and we will use the minicom to get stuff working, just to make sure that we can even talk to it and the module is not broken. So just boom, and, you can have a look at this. Okay, so we can talk with the PC over serial. So right now we're going to be hooking up the ESP01S to the serial cable. Okay, so we have a ground here. So how do we do this? Okay, so we have to disable this. Right now we stay to the ground, so what the pinout is here. So the power, we can grab it from our power supply board, from here. The ground is the gray, so that's below. Oh, we have a flashing light. So we have RX, which is the different gray. What were the pins? It was the A10 and A9. So yeah, that's a RX, and the TX is the blue one. So if needs be, we can just swap it out. And should we be extra careful and hooked up the reset as well? Okay, let's hook it up to 3.3 volt. Probably should do this through a resistor, but this is a regulated power supply, so I think we should be okay. And then our enable pin, which is this, that should be 3.3 as well. Okay, this one is not needed. No, but I actually did something extremely silly, and I hooked it up to our microcontroller when I said that we need to do this here first. So reset, it's here, like that. So what was it? RX was the gray. Okay, so here, and TX was the blue. Boom. And so that's hooked up. And we're going to disconnect our microcontroller as well. Do you see this? We're talking to it right away. Ready. So we should be able to just boom, talk to it. 80. It should just respond. Is it too fast? Well, no, we can read the ready. So the baud rate is correct. Should we add a line feed? We are adding it, I think. So 80. Add carriage return. Yeah, because the 80 commands should be what's the word? Terminated with the line feed and the carriage return. So you. So 80. Oh, come on, man. What's going on here? So the fact that we can see ready, that's definitely being sent from the module. So that means our baud rates are fine. So serial port. So there's F, which is hardware flow control, but that definitely should be disabled, because if we were to enable this, we would need to hook it up the rest of the. Basically, the Minicom would then expect that the rest of the pins from the RS-232 standards are hooked up, which is the clear to send, blah blah blah. So that's definitely not. The software flow controller, actually I'm not sure what that would do. And we're not using the RS-485. So there's definitely, so that's literally anything that we can change in here. So that's wrong. We want that. No, something's not right. One more time. So see, that's scrambled. So so 80 is enough. It should respond with like okay, or what was it, like ESP01 has 80 commands. Expects carriage return and a line feed, but just CR seem to work too, and that's not what we're seeing. And I enabled this, and I enabled this. Terminal settings. ANSI. So actually I'm not sure what's going on. So what can we do here? So let's hook it up to the, I don't know how we do this. Let's hook it up to our microcontroller. But not this. Let's hook our serial to microcontroller. And read what the Minicom is sending. Okay, so Oh yeah, I need to plug in the ST-Link back on. So that's our hello. So once we press enter, so it's 13. So ASCII table. So 13 seems correct. That's carriage return, yeah? That's carriage return. So it only sends one. But it's not sending line feed. So add line feed IA. Will that change? Are we actually sending? So it only sends the carriage return still. So that's our problem. Keyboard. P, add line feed. Yes. And yes. Seems that our thing is busted. Can we trust our code here? Like there's nothing. What's the keyboard shortcut for carriage return? Keys like that. What I'm looking for is there an explicit way to send a carriage return with the key apart from the enter key? Carriage return keyboard. Combination. There was a yeah, like Control A. To insert carriage returning bash, you would press Ctrl V, then Ctrl M. Like Ctrl M. Oh, Ctrl M, it's actually sending. In here. So that's 13. That's what it is. Control J is 10. So hello, Control M is the new line. Or yeah. So Control J is the new line. Control M is the return. Okay, so let's go back here. Like this. Did I reverse it? Yes, I reversed it. Now we're not reading anything at all. Why? They changed some settings. Let's reset it. There it is. Okay, we're talking. So that means we need to type in AT, Control M, shit, Control M, Control J. Boom. So that means that the minicom is lying to us when it says it sends stuff. So we need AT, Control M, Control J. Okay. What else we have? Yeah, that might be useful. So AT RST. So that's what reset. What does it mean reset? It just reboots it, yeah. So AT plus RST. Okie dokie. What's the other one? AT GMR. AT plus GMR. No, what have I done? AT plus GMR. Boom. Oh Jesus, are we talking to it or what? Disable echo. No, we're okay with echo. AT CW mode. 5 so AT plus CW mode. Why is it error? AT plus CW mode. Oh, there was a question mark. Because if we're querying, yeah, we need to add the question mark. So question mark, Control M, Control J. it's 2, which is AP mode, so access point mode. So that means we connect to it. So we don't want it. We want it as a station mode. Yeah, we want it as a station mode because I will connect to my local Wi-Fi in here. So AT plus CW mode 1. Okay. So if we AT plus CW mode, yes, and it's mode 1. So we should be able to query it now, right? So okay, this no AP. What is it checking? Connect to AP. Yeah, we want to list the first. Okay, I'm gonna have to wrap it up in a second. Cause we need to pick up a daughter from grandparents. Okay, so I guess we will just continue it at some stage later on. Yeah, okie dokie. So at least we have this stuff working, so we can talk to our module, and we have the serial working on the blackboard, or the black pill, should I say. So I guess we'll just continue it at some stage. Maybe tomorrow, actually. Yeah, we'll see. Anyway, bye bye.